Okay, so welcome back, everybody. All right, and so last time we had this. Let me pull it up. So we were basically going through the various applications of our separations of variables algorithm. So going through and seeing how this applied to all of the different kinds of combinations of boundary conditions we could have. So we're not going to completely exhaust this, but I did want to cover, most of the reasonable combinations of things that we've seen before. So I think what we did last were mixed boundary conditions, so that it makes sense to talk about mixed inhomogeneous boundary conditions. And so that's my next application of this stuff. So mixed inhomogeneous boundary conditions. Okay, and so um, let's do this for the heat equation, just for simplicity's sake, and this same sort of method you could think about how that would work for the wave equation. So let's look at heat equation. So u sub t is alpha, u sub xx in uh, some finite domain 0 to L, and t greater than 0. Let's say that I have mixed inhomogeneous boundary conditions, so we'll say that I have zero flux, but at one of the ends I have some inhomogeneous um, constant. So let's see here. So let's say that the flux at the left end is 0, and say heat at the right end is T naught. Okay, and so that's for all t positive. And then we have an initial condition, phi. Okay. All right. And so, question is what to do here. So we had methods for dealing with this sort of thing before. For like inhomogeneous Dirichlet, if you remember, what we did was we sought a transient solution separately, right, from a steady state solution. So we first sought a steady state solution, which is like long term or end behavior solution for this thing. So that's also what we're going to do here. So first, we seek steady state solution. So this is the long term, right? Limit. So limit as t goes to infinity of u of xt. Call that thing v of x, since this is no longer going to depend on t. Okay, if this is going to solve this, then this v double prime is equal to 0, right? V double prime is equal to 0. These boundary conditions for the steady state solution give us v prime of 0 is 0, and v of L is equal to t naught. All right, so those are my conditions on this ODE for v. So the general solution of this ODE is v of x is constant times x plus constant, right? We'll say ax plus b. Okay. But then these conditions here, right? V prime of 0 is a. But I know that v prime of 0 is also 0 from this condition, so a has to be 0. Maybe I should box this whole thing. Okay, and v of L is t naught. Right, so v of L is what here? So v of L has to be t naught. Okay. Well, v of L would be AL plus B, but A is 0 from this first bit, right? So that's 0. So this is just B, so B has to be T naught. And so all of this together tells me that V of X is the constant function T naught. That's my steady state solution. Okay. And so, so what do I do with this? Well, the exact same thing that I sought to do in the previous inhomogeneous case was I wanted to use a steady state solution. Think of subtracting it off from the solution itself, which gives me the transient solution, right? So this v of x is the steady state solution. Then the transient solution we'll call it w of xt. This is defined to be the solution, u of xt, to the above problem, with the steady state solution subtracted off, right? This was the idea. And the idea of subtracting this off, so one, why is this the transient solution? Why is this the part of the solution that moves, right? Because, well, you have taken the solution itself and you subtracted off the part of it that is steady, right? Okay. And so, what was the idea of doing this algebraically, right? So forget about the physical implications for a second. What's the reason to do this algebraically? It's just so that, one, you're abusing the fact that this equation is linear. Okay, so linear combinations of solutions to things like this are, they respect the equation or the equation respects them. And so I'm going to get something that solves the same equation, except now this is going to adjust the boundary conditions. Right, it's going to adjust the boundary conditions and initial condition. Okay, so what does this solve, right? So this thing solves what? So you can just check directly that w sub t is alpha w sub xx. So we did this before. So this definitely solves w sub t is equal to alpha w sub xx on the region in question. Okay, but what are the boundary conditions? Well, at the left end, what is the flux? The flux is going to be u sub x minus v prime at 0. So this is going to be u sub x at 0t minus v prime at 0t. They're both 0, so it's going to be 0 minus 0, so it's 0. At the right end, this is going to be wlt. This would be ult minus v of l. U of lt is t naught. V of l is also t naught. So this is going to be t naught minus t naught, so that's going to also be 0. And then the initial condition is going to be, so w of x 0 is going to be u of x 0, which is phi, minus v of 0, which is v of 0 is b, it's t naught, right? Which is actually just v of x. So this is going to be, sorry. This is v of x regardless of what it is, because there's no t here. So I'm not plugging in anything to v. So w of x 0 is u of x 0 minus v of x. So this is going to be phi of x minus v of x. It doesn't matter what particular form v takes. This doesn't depend on t. So that's always going to be phi of x minus v of x in that case. And so what is putting all these things together, right? So w of xt, which I'll remind you, is u of xt minus v of x. This solves the PDE with boundary conditions. So w sub t is alpha w sub xx. W sub x 0t is 0, and that is the same as w of lt. This is also 0 now. Okay, and the initial condition w of x0 is phi of x minus v of x. Okay. And so now we solve this. So for this, see last lecture, since this is a homogeneous mixed BC problem, which we had added to our list. We're talking about eigenvalue problems. Right, this was on our list. This is the last one we added. So recall, we added this to the list for eigenvalue problems when we have mixed boundary conditions. These are the eigenvalues and eigenfunctions, and the corresponding Fourier series look like this. Okay. All right. Okay. And so that's how we do this. Of course, physically, you can ask yourself, does it make sense that the steady state solution here is T naught, right? Given the physical description of what's going on, I think you can convince yourself of that. And so anyway, we know how to solve this problem now. So once we have solved for, say we use separation of variables to solve for w of xt, then our solution u of xt equals w of xt plus v of x. So we just add the steady state solution to w, the transient solution, and that gives us the solution to the problem that we originally sought. So the solution to this PDE. Okay. Now, you might have seen that, we kind of immediately went to a discussion of, we did homogeneous Neumann condition, but then we did like immediately, we did mixed and periodic boundary conditions, and then we did inhomogeneous Dirichlet. But we haven't actually done the complete general case of inhomogeneous Neumann conditions, right? And so maybe we'll do that next. So inhomogeneous Neumann conditions. So problem we want to look at is u sub t is alpha u sub xx. Okay, on the usual domain, my boundary conditions are now inhomogeneous Neumann. So I have flux at the left end that's prescribed to be some constant A. We'll say I have flux at the right end that's prescribed to be some constant B. Okay. I have initial conditions. Right, our initial condition, a single initial condition. U of x0 is phi of x, right? As usual. Now, you could ask yourself, in all of these cases when you said inhomogeneous, these things were still just constants, right? Whereas kind of maybe a more general case is that these quantities could just be functions of t, right, that are not constant. So how would I deal with that? there are methods of dealing with this, and maybe you deriving one of those methods might be the topic, or might be a topic on your final exam, with a nice procedure laid out for you. So imagine instead that these conditions were, this was A of t, B of t, where A and B were functions of t, right, rather than constants. And there's a procedure you can do that allows you to handle such things. So you can generalize this process a little bit. Okay, but before we do that, let's do the case of constants first, so you can see kind of how this works. Recall what this means physically, right? So you're prescribing the flux, right, to be different rates, we'll say, at the ends, okay, but nevertheless they're still both constants, okay? So we're pumping or removing heat from the bar at these prescribed rates, right, A and B, at the left and right ends respectively. Okay, so let's do the same thing that we tried to do before with inhomogeneous Dirichlet and mixed conditions, which is looking at steady-state solution. So first, we seek steady-state solution. Right, so this is limit t go to infinity of u of xt, which we have defined to be v of x. Okay, so as before, right, v of x has the expression a plus bx. I think I wrote it as ax plus b before, but that's fine. So it has a plus bx is general form of this thing. But now I want to compose, I want to impose the initial conditions here. So how would I do this, right? So I am taking derivative of v at both ends, so this would be, so v prime of 0 is a, and v prime of L is B. Okay. V prime, sorry, maybe I should, hold on. We've been a little bit confusing here. I used A and B up here, but then I used the same A and B constants here. Okay. Let's not do the bad thing. Let's use different constants here. So C1 x plus C2. There we go. All right. Now we're happier. Now we didn't do something bad. Okay. Okay, and so if v prime, so v prime of x, of course, is going to be C1. So v prime equals 0 being a, so a is v prime of 0, but v prime of 0, of course, is C1, but v prime of 0 is also, or sorry, v prime of 0 is the same as v prime of L, right? Because this is constant, so v prime of 0 and v prime of L are the same, but v prime of L is B. And so both A and B have to be C1, or C1 has to be both A and B have to be equal for this to have a solution. But here's the problem, right? So even if this was true, even if A was equal to B, then all that would tell us is that v of x would be, so A and B would have to be equal, and also they have to be C1, this constant here. This would be like A or B, whatever you want to write here, x plus C2, and I don't know how to determine this thing, right? I don't know how to determine that constant. And all of this, of course, is because you had Neumann conditions, right, on the derivative, and you had no condition on v itself. So what's the problem here, right? What do I do? How can I determine this thing? I have to be able to determine this for this to make sense. So what do I do? Well, here the idea is instead of resigning myself, that's a funny way of looking at it, to finding a steady state solution, what if I instead seek a particular solution to the PDE that is not necessarily the steady state solution? And when I say a particular solution to PDE, I mean PDE plus these Neumann boundary conditions. Okay, so particular solution here means exactly what particular solution meant in your ODE class. So particular solution to a differential equation just means any old solution, anything that satisfies it in the boundary conditions. So we're not making a claim that it's a general solution, right? The general solution to an ODE or PDE means that it's the form that any solution has to take, right? So we're not making any claims about that. We're saying this is just a solution, right? Something that solves the PDE in boundary conditions. Well, how do I do that, right? So I think about the PDE for a second and I ask myself whether or not it makes sense to seek solutions in a particular form, right? And so the idea is to seek a particular solution, v of xt, of the form ax squared plus bx plus ct. What is like your idea here, right? Well, looking at the PDE itself, this is defined in such a way that for the second order x partial, the only thing that's going to be left here are constants. And for the t partial, the same is true, right? So in the derivatives that show up, I have constants that are left. And so a PDE, or satisfying this PDE, is going to give us some relation between the constants that would make that work. And so we know that choosing it to be a solution of this form, we're going to be able to make this work by just making particular choices on the constants here, right? This would be, we wouldn't have any hope of doing this necessarily if we had chosen a slightly different, even polynomial form of this thing, okay? All right, that would require too many other assumptions. And so that's our first idea. Now, if we want this to satisfy the PDE, u sub t equals alpha u sub xx. So if this is going to satisfy u sub t is equal to alpha u sub xx, then what does that mean, right? Of course, we also want it to satisfy the boundary conditions too. So plus BC's, which are u sub x0 of t is a, and u sub xl of t is b. Then, first of all, what is v sub t? V sub t is c, and alpha v sub xx is alpha times v sub xx, so v sub x is going to be 2ax plus b. So it's going to be 2a. Right. Okay. So this immediately says that C, so if Vt is going to be equal to alpha V sub xx, then C needs to equal 2 alpha A, right? So this is going to need, so C, um, C has to be equal to 2 alpha A, and that's the first relation I get to make sure that this works. Okay. So then if C is 2 alpha A, then so our v of xt is ax squared plus bx plus 2 alpha a t. So this thing solves the PDE, and now it's time to impose these boundary conditions. So here v sub x of xt is what? This is going to be 2ax plus b. And so we have to impose the boundary condition at x equals 0, which is a. So v sub x 0t, that needs to be a, but here that is b. Okay. And then v sub x at x equals L, this has to be b. But the other form this takes is 2a L plus little b, which is a. Okay. So then little b has to be a, little c has to be 2 alpha little a, and little a solving here, this tells me that little a is b minus a over 2l. So putting C entirely in terms of big B and A, this means that C is 2 alpha times A, so this is 2 alpha times B minus A over 2L. Okay, we could simplify that a little bit if you really wanted to. And so what this means is that following this form here, v of xt is little ax squared plus little bx plus 2 alpha at. And so what that leads to, now that we solve for all these things, is that, so v of xt is b minus a over 2l times x squared plus ax plus 2 alpha times b minus a over 2l t. This solves the PDE, and so this solves PDE plus boundary conditions. Okay. Okay. Now we define w of xt such that u of xt is w of xt plus v of xt. Okay. And since we want this u to solve, I'm going to put the equation back on the board, or back on the camera here. So we want it to solve this thing. Right? This was the thing we were trying to solve. Then what should this w solve? We know that v solves this PDE plus these boundary conditions, right? But we haven't imposed any initial condition on v. So then what should w solve? Recall, this would mean that w is u minus v. As before, take advantage of the linearity here. W should solve the same PDE, but now what are the boundary conditions going to be? Well, if W and V both solve these boundary conditions, then subtracting them off here at the boundary, I'm going to get homogeneous Neumann conditions. And then the initial condition is going to be phi of x minus the initial condition on V, or the initial value of V, which is going to be V of x0. Right? So, since we want U to solve asterisk, this means W solves the equation W sub t equals alpha W sub xx on our finite domain. Okay, then with homogeneous Neumann conditions. On the boundary, and initial condition w of x0, which is u of x0 minus v of x0, but u of x0 is phi, so this is phi of x minus v of x0. V of x0, of course, is, we plug in t equals 0 here, we get b minus a over 2l times x squared plus ax. Right? So this is 0 x minus l, and of course, yeah, just note that v of x0 here is b minus a over 2l x squared plus ax. This is a homogeneous Neumann problem, right? This is now a homogeneous Neumann problem that we've solved before. So we previously solved this. You might remember that we get the Fourier cosine series instead, so just reminding you from our list of eigenvalue problems. For Neumann boundary conditions, the associated eigenvalue problem, once you separate the variables, is this thing. There's the Neumann boundary conditions that have descended to the boundary conditions for the eigenvalue problem. And so this leads to eigenfunctions and eigenvalues here. And the Fourier series involves the Fourier cosine series. Okay, so we already know how to solve that. And thus, that's exactly what we do. So we solve exactly that, except now instead of having phi of x as our initial condition here, we have this extra minus v of x0 term, this thing. Okay, but apart from that, everything else is the same as when we first solved this kind of problem. Okay, and so you can make a lot of use out of some simple algebra dealing with these solutions. And I want to stress that all of this is because the equation in question is linear. Right? That's what allows these linear combinations of solutions. It allows you to basically pick apart the conditions that you want, the boundary conditions you want, and kind of reassemble a solution satisfying a slightly different boundary condition. Right? This is really the key behind linear equations. And again, this is all the principle of superposition. Right? Okay. And so, let's keep going here. So we have done pretty much every combination of our typical boundary conditions. So we did Dirichlet, both homogeneous and inhomogeneous. Neumann, both homogeneous and inhomogeneous now. Mixed, both homogeneous and inhomogeneous. And we did periodic boundary conditions. So all of the four boundary conditions that we talked about, we have done. But there was another boundary condition type that we discussed for both the wave equation and the heat equation, and this was the Robin boundary condition. This is a little bit more complicated, so let's do Robin boundary conditions for diffusion equation. Recall, if you want to, the physical interpretation of these sorts of boundary conditions. We made sense of these via Newton's law of cooling, rewriting the boundary condition as a statement about flux being proportional to the heat in the region or at the end in question. And so this is the diffusion equation, so U sub t is alpha U sub xx on our domain as usual. Let's say that at the left end we have homogeneous, like Dirichlet condition, and at the right we have this Robin condition. There's other combinations of the Robin condition that you can address, but all of them are going to be similar to this one. So here's one. Let's let L equal 1. Let's take L equal to 1 just to simplify this. So maybe rewrite this L as a 1 here. This Robin condition, we'll say U of 1 t plus U sub x, 1 t is equal to 0. And that's for t positive. And then I have an initial condition like usual. Okay. All right, so here's my Robin condition. Now, let's use separation of variables, right? So for separation of variables, what do I do? Right, so I seek solution u of xt that looks like x of xt of t. I go through this whole process. I get eigenvalue problems. My eigenvalue problems are going to be, the first one is going to be x double prime plus lambda x is equal to 0, the usual one. The other one is going to be t prime plus lambda alpha t is equal to 0. Okay. And so now what? Well, I didn't impose the boundary conditions here, so here I don't get any. I just have my condition or my equation for t. For this one, these boundary conditions descend to boundary conditions for this eigenvalue problem that are x of 0 is equal to 0. That's one of them. But the other one is x of 1 plus x prime of 1 is equal to 0. And so I have this eigenvalue problem. Well, let's just quickly check our list. All right, you already know the answer here. But what does our list allow us to solve in terms of eigenvalue problems? Well, I can solve Dirichlet boundary condition eigenvalue problems. Okay, this isn't one of those, so that's gone. Neumann condition problems. This isn't one of those either, so that's gone. Periodic boundary condition problems, but this is not one of those. Okay. And mixed boundary conditions. I mean, it kind of looks like it is, but it's not really, right? This isn't the same kind of thing going on. Okay. And so this isn't on my list. Right? This is not on my list. This is not on my list of eigenvalue problems that I already know how to solve. And so I'm going to have to find out how to solve this thing on my own, right? Well, what did I do in these cases? In fact, we only did it fully for the Dirichlet case, but it works similarly for the rest. What did we do here to generate these solutions? So let's go all the way back to the Dirichlet case. What do we do here? Well, we actually just noted, okay, this is like from ODE class. I know what this needs to look like. It depends on what case I'm in, right? Since I know this general fact that lambda has to be real, since it's real, then I know that the only possibilities are lambda is either negative, 0, or positive, right? And so if lambda was allowed to be negative, that would lead to certain form solutions, but usually I can rule that out for some of these. So usually there's no negative eigenvalues, and then there's 0 or positive eigenvalues, and if I'm in that case, then my solution has particular forms it takes, right? So sines and cosines show up oftentimes here, right? In fact, when lambda is positive, that's exactly what happens. We can apply that same reasoning because, after all, this is the same ODE. It's the boundary conditions that are different, right? Which might not seem like much at first, but we know the difference it can make in just kind of just slightly changing these boundary conditions, because that ultimately changes how these solutions are determined. But the underlying ODE is the same, and through similar reasoning, I can apply that to this equation and say, I only get the I only get the positive eigenvalues here. Okay, and so so let's have a look at this, right? So here's the situation I'm in. So similarly to some, not all, some previous computations, here I get eigenvalues that are positive, i.e. the form that x of x takes is a sine of square root of lambda x plus b cosine of square root of lambda x. Right. So this is the form the solution takes. Now I want to impose these initial conditions. Well, if x of 0 is 0, then when I plug in 0 here, I get a times sine 0, so a times 0, that's 0, plus b times cosine 0. B times cosine 0 is just b, since cosine 0 is 1. So b has to be equal to 0. Okay. Not too bad. So this implies that my eigenfunction looks like this. That's not bad at all, right? That's pretty cool. And that was imposing this boundary condition, right? Okay. Now I want to impose the other boundary condition, right? The other BC. The thing that makes this a row beam boundary condition problem. The other boundary condition is x of 1 plus x prime of 1 is equal to 0. So then x of, let's see here, so x of 1 is a sine of square root lambda, and x prime of 1 is a times square root of lambda times cosine of square root lambda. So this condition implies that a sine square root lambda plus a square root lambda times cosine of square root lambda is equal to 0. So I can divide both sides by a, and I can move one of these over. So this would tell me that sine of square root lambda is equal to minus square root lambda times cosine of square root lambda, or that dividing through by cosine square root of lambda, I would get tangent of square root of lambda is equal to minus square root lambda. Okay. I can move the minus sign over here for simplicity's sake for the graph that I'm going to show. But let's let alpha be equal to square root lambda, right? Or since we used alpha in our heat equation, we'll just say let let y be equal to not minus square root lambda. We'll say square root lambda. Then what we're doing is we want to look for intersections between two functions, right? So I'll rewrite this as minus tan y is equal to y, right? So I have minus tan y. I know what that looks like, right? This is like looks like that, and y looks like this. Okay. And so what does this tell me? Since there's infinitely many of these intersections, ultimately I get infinitely many eigenvalues determined in exactly this way, right? So these intersections are my eigenvalues. Because don't lose sight of what we're doing here, right? Because ultimately what we're doing is the actual form the eigenfunctions take is relatively simple. It's this thing. But then this second boundary condition has led to a relation on the eigenvalues, say they have to satisfy this thing. If I actually plot out what this thing is, the points that satisfy this equation arise as intersections of these two things. Let me show you the picture in the textbook of this. So let's see here. Okay, yep, here we go. So there we go. the graphs of y equals alpha and y equals minus tan alpha. This should say alpha here. I think the graph in here, this looks right. There we go. So alpha and minus tan alpha is plotted here. These intersections are points where that relation is satisfied. And that's how I get my eigenvalues. But there's a problem here, right? So there's a problem. The problem is that there's no closed form for these eigenvalues. In fact, these have to be approximated, right? But there is one problem. Okay, and maybe I should say it's quote problem, because I'll show you how we'll deal with it. So here, in this case, there is no closed form expression for the eigenvalues. Now you could say, well, can't I just write the eigenvalues as a symbol, right? They're lambda. And so I write them in my problem, and then the understanding is that these eigenvalues lambda are generated, right, via this relation that I've written out. So they have to satisfy this relation, and that's what they are. But that's not a closed form expression, right? Before we had things like lambda sub n is, n pi over L all squared, right? That was our that was our expression for lambda. We don't have that kind of thing here, okay? And so what we get instead are the following. So instead, we must approximate these eigenvalues lambda. Okay. And so, just for example, lambda 1 is approximately like 4.116, and lambda 2 is approximately 24.14, and lambda 3 is approximately 63.66, and so on, where lambda sub n is approximately 2n minus 1 squared pi squared over 4. Okay, and you can check that those are indeed approximately this thing. This is for the higher ones, though. We'll say n equals 4, 5, 6, and so on. Okay. Then my corresponding eigenfunctions, well, we found what those are. Right? So my corresponding eigenfunctions are a sine of square root lambda x. So I can choose a to be 1 here. I don't care, right? So x sub n of x is sine of square root of lambda n times x. Right? That's for n equals 1, 2, 3, and so on. Now we can finish using separation of variables as we did before. So how does this work? Well, remember, that's our eigenvalue problem taken care of for x. The eigenvalue problem for t is easier now that we have found these eigenvalues. Right? So now this yields, right, eigenfunctions for t that look like what? We're using these eigenvalues, right? And so the t eigenfunctions are what? This is e to the minus lambda n alpha t here. Okay. So then my solution is of the form Thus, my solution u of xt is of the form u of xt is the sum from 1 to infinity of some coefficients b sub n times sine of square root of lambda n x e to the minus lambda n alpha t. Okay, there it is, where the b sub n are some undetermined coefficients. So the question we always asked, and our answer was usually given pretty readily just from all of the previous Fourier series and eigenvalue problem stuff that we had done. And so the question is, can we choose b sub n such that the initial conditions hold, i.e., what we want is that u of x0 is phi of x, which is a sum from n equals 1 to infinity of b sub n sine of square root of lambda n x, right, because I'm plugging in t equals 0 here. And the answer is yes, which you might regard as a miracle, but actually we have already more or less determined how this works, right? So how does this work, right? B sub n for a general Fourier series, right? B sub n is phi paired with the x sub n's over x sub n paired with itself. And so what is this? This is 1 over x sub n paired with itself here times the integral from 0 to 1 of phi of x times x sub n, right? So this is sine of square root of lambda n x dx. What is x sub n paired with itself? So x sub n paired with itself, you can check by direct integration, right? For this is, remember, check for L equals 1 here, right? That's the case we're doing. Check that this is actually equal to 1 plus cosine squared lambda n over 2. And so what we get here for B is that this is 2 over 1 plus cosine squared lambda n times the integral from 0 to 1 phi of x sine of square root of lambda n x dx. So this was a little messier than the other boundary conditions we've done. Right? This is our first example where we weren't actually able to find a closed form expression for those eigenvalues. But nevertheless, right, proceeding with an approximation of those eigenvalues, we were still able to do this in a similar way. And the resulting coefficients here now weren't necessarily from a Fourier series that we recognize by name. But if we use this formulation of general Fourier series here, the answer was still yes. And ultimately, we were still able to figure out how this thing worked. Of course, all these lambda n's here are generated by that formula, right, that we obtained from this relation that it had to satisfy, right? Okay, so this thing, maybe I should show here. Okay. All right. Now, let's do a quick revisit of Duhamel's principle. So revisiting Duhamel's principle. Okay. So this is kind of our next, now that I feel like we've done pretty much all possible combinations of boundary conditions that we're interested in for now, we'll see how all of that work we did in those cases can be slightly generalized now by considering inhomogeneous boundary conditions where instead of having constants, maybe we have functions of t there instead. So that will be a route of investigation, as I said, for some problems that you do maybe on your take-home final. And so, what about Duhamel's principle? So I want to apply separation of variables in a way that lets me deal with source terms for a boundary value problem. Right? So remember Duhamel's principle. So recall Duhamel's principle allowed us to deal with source terms. So I'm going to choose Dirichlet conditions here instead, but we could talk about this for other types of boundary conditions, but I'm just going to do this for the Dirichlet case. So consider the Dirichlet BVP for the following. So this is a diffusion equation with a source term. So u sub t equals alpha u sub xx plus some function f of xt. That's our source term. The typical domain is the one we're on. And we have homogeneous Dirichlet boundary conditions. Okay, and that's for t positive. And then we have some initial conditions. So this is the thing that we want to solve. Maybe I'll call this star. So this is the thing that we want to solve. What was kind of our motivation behind Duhamel's principle for dealing with something like this? The idea was it's going to be the same as it always was for all of these cases. Right, so we first saw Duhamel's principle for the wave equation. We just kind of did it without much motivation. And then later we saw it again for the heat equation, where I didn't really go through the full justification for why you should expect this to work. Kind of algebraically and mechanically we went through why it has to work, and you may have been required to check that it does in fact work on some previous problems. We didn't really get too much into like the physical reason why Duhamel's principle might work. The idea, though, is the same as it was before, which is that I use the fact that this is a linear equation, and I use superposition to say what I can do instead is actually solve the completely homogeneous problem in the sense that even the initial condition is 0, and then add it to a solution where I don't have a source term. So the idea is by superposition, first solve the PDE u sub t is equal to alpha u sub xx plus f of xt with 0 initial and boundary conditions. Okay, so both initial and boundary conditions are 0 here. And if I can solve this, so solve this equation and add it to the solution to the equation that is now lacking a source term entirely, but is our usual initial value problem, right, for the Dirichlet boundary conditions. So the reason why this ends my search for a solution is that I know how to solve this, right? I know how to solve this with separation of variables. So I know how to solve this with separation of variables. And so, really, all I have to do, rather than solving this completely general problem, I can solve this simpler problem that still has a source term, but now has 0 boundary conditions and initial condition. So then this is the thing that I want to solve. Let's call this asterisk here. Okay. So I've taken my problem of solving star and reduced it to a problem where all I have to do is solve asterisk and then add it to a solution to this problem, which I already know how to do. Okay. All right. So then it's Duhamel's principle that's invoked to solve this asterisk problem. Okay, so by Duhamel's principle, states that in order to solve asterisk, okay, so in order to solve this asterisk problem, for any s greater than 0, I consider a solution that I write u of xt with this new parameter s. So I consider a solution u to the following IVP BVP, which is u sub t xts is equal to alpha u sub xx xts, where x lives in the same place, but now my initial value is t equals s. So this is for t greater than s. My boundary conditions are still 0 here. So this is 0 t s. That's 0. And this is u of l t s is also 0. And again, that's for t greater than s. My initial condition is, of course, like I said, at t equals s. So the initial condition is u of x s s is now given by the source term, right? And this is for x everywhere on my interval. So I consider a solution to this. Maybe I'll call this smiley face. Okay. And then my solution to asterisk is given by integrating this solution over the parameter s from 0 to t. This was Duhamel's principle. And the thing is that this can seem a bit mysterious, right? But you can verify just from like rules of calculus, right? And actually just plugging it into the equation, being very careful here, you can verify that this works. Okay, like I said, you've actually had to do that previously for various problems. So you can actually verify that this solution formula, so this thing solves asterisk, And we take that solution and add it to our usual solution that we did via separation of variables for Dirichlet, homogeneous Dirichlet boundary condition diffusion equation problems. We add those together and we get a solution to this problem with source term. So this allows us to deal with that source term. Okay? And so we can actually check. Now, let's do this via separation of variables as we did before, right? So now we have smiley face. And guess what? Smiley face is what kind of equation? It's a heat equation with homogeneous Dirichlet boundary conditions with some initial data. So let us solve smiley face now via separation of variables. How do we do this, right? Well, I know exactly how to solve it. Again, this is a heat equation. It's homogeneous Dirichlet boundary conditions with my initial data given by this f. So how does this work? Well, for each, the only difference here between this and what I have before is that I have this parameter s floating around. How does that impact my solution? So for each s greater than 0, what do I get? For x in, say, r and t greater than or equal to s, what does my solution look like? U of x, t, s is an infinite sum from n equals 1 to infinity of some coefficients here that are actually going to depend on s. Sine of n pi x over L times e to the minus alpha n pi over L all squared times t minus s. Oh, there's no ds here. There's no integral. Okay. What is this? What is this? These coefficients now depend on s. How can I interpret that? Well, where did I get my coefficients before? My coefficients before were, in this case, right, this would have come from like the Fourier sine series, right? So I would have integrated phi against these eigenfunctions, these sine eigenfunctions. Here, now I don't have a phi of x, I have an f of xs that depends on x and this parameter s. So that's why these coefficients now depend on s. What is the formula for them? Right, where b sub n of s are equal to, well, what was the formula for the b sub n's normally? Right, this was 2 over L times the integral from 0 to L of phi of x, right? That was our initial condition phi. But I don't have an initial function phi here. I have this thing, this f of xs. And so, for each s, I have this integral, right? F of xs here is the thing that goes right here, times these eigenfunctions, sine of n pi x over L dx. And so that is indeed this is my solution formula, like taking these things and putting them together. This gives me my solution. Now, if I wanted to write this in a nice form as a sum of infinitely many of these integrated things here, I just have to make sure that all the convergence is going to work out that allows me to swap the order here. But let's say that that's fine. Then, thus, my solution to this original, since my solution to asterisk is given by integrating with respect to this parameter s from 0 to t. An asterisk, of course, solves this completely homogeneous problem with source term. Now, my u of xt, right, is, so u, that's my solution, u of xt is, by Duhamel's principle, u of xt is the integral from 0 to t of u of xts ds. Well, what is that thing? U of xts is given by this formula here, right? And so this is the integral from 0 to t of the sum from n equals 1 to infinity of b sub n of s sine of n pi x over L e to the minus alpha n pi over L squared t minus s ds. Okay. I can, this, only the things that involve s here matter to this integral, so I can pull those out. I can pull this sum out. So this is the sum from n equals 1 to infinity of sine of n pi x over L times the integral from 0 to t of b sub n of s e to the minus alpha n pi over L squared t minus s ds. This is my u of xt that solves, so this solves asterisk, which is here. Thus, a solution to my original problem is this solution I've written down here, added to the previous solution of homogeneous Dirichlet boundary conditions diffusion equation. So my solution to star is obtained by adding this to the general solution to the usual heat equation with Dirichlet BCs, homogeneous Dirichlet BCs, and my initial condition, or my initial data function phi, sorry. Okay. Okay. So that is an application of separation of variables to Duhamel's principle that allows us to solve that parameterized problem. Now, one thing I could say is notice, right, up until now, we have only done two of the big three with our separation of variables algorithm. Okay. And so the question is, what happened to the other one, right? Why haven't we talked about the other one? So, in a weird way, as I've mentioned before, Laplace's equation requires a little bit of it requires a little bit of finesse, because while all the equations we've involved, right, have been finding solution for a PDE. It's a PDE, so there's at least two independent variables that are involved here, right, for in our solution function. But because the variables were one spatial variable and one time variable, it meant that the boundary conditions, right, the boundary value problems involved boundaries that were zero dimensional, right? So it's one spatial dimension, so our x lives in an interval, but the boundary of an interval is just two endpoints, right? So with Laplace's equation, because Laplace's equation is for, in at least the 2D case, is for now a two-dimensional region, right? But the two-dimensional Laplace's equation is the analog of, say, the one-dimensional heat equation or the one-dimensional wave equation. And so what does this mean? It means that now our boundary is one-dimensional. Our boundary is like a curve, for instance, right? So, question, what about Laplace's equation? And the answer is we'll do it in the next lecture. So we'll do it in tomorrow's lecture. And specifically, the idea here is, let's say that I have Laplace's equation. So Laplace u equals 0, and then on the boundary, right, I have some function, right? So on the boundary, so u restricted to, so this will say is true on some d, some region d, maybe. Here's x, here's y. My region D might look like this, right? Here's my region D. It's my 2D region. And then on the boundary, right, so u equals, say, some function g on the boundary of D, which of course is this curve in this case. Right, here's the boundary. So I have Laplace's equation, of course. This is, I could just rewrite this as u sub xx plus u sub yy equals 0 on region D, and u equals g on the boundary of D, where g is my prescribed function. Now this is my boundary condition. There are no initial conditions because this is Laplace's equation, right? There's no t. Okay. And so you might say, wait, how is this the analog of what we've been doing? Because wouldn't the Laplacian of u show up in, say, the 2D heat equation or 2D wave equation? Yes, that's true, right? But in that case, a solution would be a function of three independent variables, right? X, y, and t. So what I meant by it being an analog here is that to seek a function that depends on the same number of variables here, right? The 2D Laplace's equation is the analog of the 1D heat equation and wave equations. We're going to see how this is a complicated thing, and this very much depends. You might automatically look at this and say, wow, specifying a function, like specifying its behavior, now not just at endpoints, right? 2 points, right? You're specifying its behavior on some one-dimensional region now, so infinitely many points, right? You might say, well, that very much depends on, it depends on the function you're prescribing it to be on the boundary, and also it might depend on the boundary itself and how nasty it is, which of course depends on the region in question. And in fact, that is going to be the case, that the underlying shape of the region is going to influence what these functions look like. And so tomorrow we will start by doing this on a rectangle, right? We'll do it on a rectangle, and we'll do it on a disk, and we'll see what this results in. But anyway, that's where we'll stop for today. Tomorrow we'll do Laplace's equation, and tidy up, like I said, we'll tidy up this discussion this whole week of kind of the last applications of our separations of variables algorithm, and that will be all of the course content. That will be where the course ends. So anyway, we'll see this tomorrow. So